Hello, please confirm that you can hear me. Hello, can
Yes,
you?
sir.
Okay, thank you. Okay, please also confirm that you can see the presentation and hear me clearly. I
Yes,
hope
sir.
that, okay, thank you very much. So, um, let us see. In the last class, we talked about Euler's method, the formal theory of Euler's method, and then we began some analytical discussion on first order autonomous systems, particularly with respect to linear autonomous systems. What do I mean by linear? That if you have a function dx dt, as in this case dx dt is equal to fx, that is an autonomous system. And if f is a linear function of x, as in minus x or plus x or ax plus b, or of ax plus minus b, whatever, then you have a linear autonomous system. So we discussed the very basic example of that, whereby rate, which means dx dt, is proportional to the state. State meaning the value of the function x as it depends on t, and the time rate change of that function, the derivative of that function. Time rate changes of the function is given by dx dt. So rate is proportional to the state. That is how you should see it. Incidentally, that sort of a thing is quite important in various contexts, in physics, of course, also in banking, compound interest, and all that. This is the general form of geometric progression. Rate is proportional to the state. Okay. Uh, Now, then we moved forward to a more general linear expression, whereby you have just like, if you have y is equal to mx plus c, so it is, instead of y, you should see function of x, and that's equal to a plus minus bx. So this is a linear combination, a first order term and a zero order term, nothing higher than the first order. So that is the equation of a straight line. And we looked at the negative sign first. We have got a plus minus bx. We looked at a minus bx, but it is to be understood that both a and b are positive numbers. Right. So we carried out rescaling. These things are important because it'll help your integration. I mean, you can integrate and do all sorts of things without rescaling. That's not a problem. Uh, Not usually, but sometimes it could be. And also with respect to coding, if you can change your function to parameter-free state, it makes your coding efficiency that much higher. We shall discuss coding efficiency in due course. There are certain theory. I mean, because I've always been telling you many times, I've told you in the class that there has to be an optimization between the accuracy of your program and the efficiency of your program. For the sake of accuracy, you must not sacrifice efficiency. And for the sake of efficiency, you must not sacrifice accuracy. So there has to be a yardstick. So we'll discuss all that. Anyway, so I'll come to all that later. So we freed this function of all parameters and got a parameter-free equation, an equation free of the two parameters a and b. Then we carried out separation of variables. There's an error over here. It should t is equal to 0. Incidentally, yesterday I admitted the whole class into the Google Classroom, so you will find all these notes in the Google Classroom. At the end of the class today, I shall have a brief discussion on that as well. So, right. Now, let's just, I mean, we found under the initial condition at t equal to 0, x is equal to 0. We shall look at this initial condition in greater detail very soon. Under the initial condition, t is equal to 0 and x is equal to 0, we found this solution. X is equal to x naught, a by b, 1 in minus e raised to minus bt. By the way, I'd like to stress something, that this equation and this initial condition has got a good deal of importance in physics. And so it is that we have a good deal of importance in physics for this equation. Dx dt is equal to minus ax, even plus ax, but more dx dt is equal to minus ax. It's like it's the radioactive decay equation. So both this equation and this equation, simple as they may look, they have got a good deal of importance in physics. We shall see about that soon enough. So anyway, so we shall now just have to, I mean, if you were working on a computer, it is very easy for you to plot a set of data or whatever you've got through your numerical integration and plot it. But occasionally, it's also helpful for you to have some understanding of the plot in your mind. So suppose I deprived you of a plotting software or a computer or anything, then how would you plot this function? That is the question. So there are ways in which, I mean, computers have been in circulation for not more than 100 years, in fact, less than that, the kind of computers that we understand it to be today. So people were plotting these things for a long time, for much longer than a computer, and far more complicated functions as well. So let's see how we can do that thing. So when you have a at t equal to 0, x is equal to 0, because at t equal to 0, e raised to 0 will be 1, 1 minus 1 will be 0. Fine. When t goes to infinity, then e raised to minus b into infinity, b being positive, e raised to minus infinity will be 0. So x will tend to a by b, as has been written over here. We found that this function has no turning point. Right. I mean, the function goes towards small x equal to a by b, and capital X will go towards 1. What is capital X? I hope you have not forgotten. Capital X is small x divided by x naught, which is a by b. So capital X has been scaled in terms of, has been obtained by scaling small x in terms of a by b. Okay. So when t goes to infinity, x goes to 1, and dx dt will go to 0. Okay, but at infinity, so that is the only situation when you have dx dt going to 0. Dx dt will be equal to 0 when x is equal to 1. And when can x be equal to 1? When t goes to infinity. Fine. But what about the second derivative? When the first derivative goes to 0, I have given you a brief theory over here, generally applicable, that for an autonomous system, which is described by dx dt is equal to fx, the second derivative will also be equal to 0 if the first derivative becomes 0. How so? Dx dt is equal to fx. Therefore, d2x dt squared will be equal to df dt. And by chain rule, you write it as df dx into dx dt, right? So if dx dt is equal to 0, then regardless of whatever df dx may be, d2x dt squared will also be equal to 0. So both the first and the second derivative will vanish. And that is not the signature of a turning point. A turning point has a vanishing first derivative, but a non-vanishing second derivative. But here we have a vanishing second derivative. Actually, it is like the behavior. I mean, if you think of a straight line has got both a I mean, has got a vanishing second derivative, right? But of course, not a vanishing first derivative. So, well, yeah, maybe I shouldn't bring in the analogy of the straight line over here because there is something else to do. But whatever it is, there is no turning point for the function. Just like a straight line also doesn't have any turning point. Maybe we can just draw the comparison up to that only and not beyond. Okay, so long time limit shows a saturation towards a long time behavior in time shows a saturation towards the limiting value of x. Uh, Short time when t is equal to 0, x is equal to 0. But when t is slightly more than 0 but very much small, how small? When capital T is very much less than 1. Note that capital T is a dimensionless quantity. I'm still discussing all these things because the basic understanding of it should be very important. How can capital T be dimensionless? Let us see. Here is our equation. Sorry. Dx dt is equal to a plus minus bx. If you look at it dimensionally, if this is dx dt, then a must have the dimension of x by t, whatever x is, right? X upon time. And so here you have x already, the dimension of bx will also be x by t, because you are adding two things. If x has the, I mean, x is there, so for balancing dimensional compatibility, b must have the dimension of 1 upon t, dx dt here and b into x here. On both sides, if you have to balance, b must have the dimension of 1 upon t. And so capital T will be equal to b, which has the dimension of 1 upon t into t. So overall, this thing is a dimensionless quantity, b into t. So b has the dimension of inverse time, right? So capital T is a dimensionless quantity, and we can expand this 1 minus capital T part by our well-known exponential formula. E raised to minus t will be 1 minus t plus t squared by factorial 2, etc. Then this 1 minus of e raised to minus t will be 1 minus of e raised to minus t. So when t is very much less than 1, remember t is a dimensionless quantity now, is very much less than 1, the higher powers can be neglected. I've discussed this feature quite a few times earlier, that when a number is very much less than 1, you can neglect its higher powers with respect to its lower powers. So the smallest lower power here is the first power t. So that will be the most dominant power. Suppose t is equal to 1 by 100. T squared will be 1 by 10,000, right? So 10,000 can be neglected against 100, like that. So we can write this, drop all these square cubic term, and we can just have 1 minus or 1 minus t, and that 1 minus 1 will cancel, and we'll just have plus t. So capital X is equal to plus t. Capital X has been defined as x divided by a by b, which is x naught is into bt. And so x naught is equal to a by b. So early growth, x is equal to at. So here, the transition is taking place. So early growth is linear. Late growth in the long time saturates towards the limiting value, and there is no turning point. How will we plot that? Early growth is linear. Late growth is saturation. And the transition from one behavior to another happens somewhere in between on some time scale. What is that time scale? That time scale is capital T is equal to 1. Capital T is equal to 1 meaning, if capital T is equal to 1, then small t into b is equal to 1. That is roughly the point where the transition takes place. Small t into b, b into small t is equal to 1. Therefore, from 0 to nearly capital T is nearly equal to 1, you'll have a linear behavior. X is equal to at, roughly that. And then beyond that, you have an exponential convergence. The convergence is like 1 minus e raised to minus bt. And so this transition is taking place at, why should I say that it is taking place at capital T is equal to 1? Because the linear behavior is valid only for capital T less than 1. As soon as capital T becomes greater than 1, then you can't neglect these higher powers of T with respect to the lower powers. So this approximation does not hold for T being greater than 1. And this approximation leads to the linear behavior in the early stages. So that approximation can't be stretched beyond the point where capital T is equal to 1. And so this is what it is. So if capital T is equal to 1, then T is equal to 1 by B. Make a note of this fact that in a system, make a note of this point, feature very carefully, because later we will come to this thing. We will also discuss these things later in greater detail when we take a physical system. That B, 1 upon B, 1 upon B is a natural time scale in this system. It's a natural time scale. Right. So the system has its own time scale, and accordingly it will adjust its dynamic behavior. Dynamic behavior as in time-dependent behavior. Just think about it. Every system has got various natural time scales. Many systems, maybe I shouldn't make a sweeping generalization and say every system, many systems. For instance, think of the human body. In the early stages, a child grows quite visibly and dramatically, right? Then there is a natural time scale in the human body which is universal. Around about the age of 17 or 18, growth comes to a stop. the 17 or 18 is also, yeah, I mean, somewhere around 15 to 18, right? So that is not a precise age, but somewhere around. So there's a bit of fuzziness about it, uncertainty about it. But around about that age, the human body starts growing, stops growing as rapidly as it was doing earlier, and then gradually saturates towards a limiting value. I just gave the human body as an example, and there are several other examples that you can think of if you sit and reflect carefully on this particular point. Um, so as you can see, then I mean the system will start growing towards the limiting value. Right. I mean, for instance, in the case of the human body, the height or the weight, these things also saturate towards the limiting value. I mean, 6 feet or 5 feet, whatever for the height. So it's not nothing like no human being suddenly grows to a height of 50 feet or 80 feet, something like that. No such thing has been known. So anyway, so when the transition takes place, what is the value of the function? So you put small t is equal to 1 by b. That's a rough value. So e raised to, this will become e raised to minus 1, as has been written over here. X is equal to x naught into 1 minus e raised to minus 1, or 1 minus 1 by e. And so that will be about, if x naught is the limiting terminal value, roughly about 60%, 0.63 of x naught, or 63% of x naught will be the phase where the system will grow quite rapidly and then it will saturate. By the way, uh, you may be surprised. I mean, many of you must be taking a keen interest in the game of cricket. And there is the Duckworth-Lewis equation for calculation of runs in a rain interrupted in an interrupted match, right? I'm just saying this for general knowledge. It's not a part of your syllabus. So the equation for the calculation of Duckworth-Lewis run rate is this, is just what you see in front of you. X is equal to x naught, 1 minus e raised to e minus bt. That is the equation that you have Duckworth-Lewis. Also, I just gave you the example of the human body, that in the early stages, there is a rapid growth, and then later the growth saturates towards the limiting value. So it is supposed that the universe, the growth of the universe is something like that. I'm not saying exactly like this. The universe, in the early stages, in fact, the universe grew exponentially. It's called the inflationary universe model. In the early stages, the universe grew very rapidly, exponentially. This one is showing a linear growth, by the way. And then later, the universe is the growth rate of the universe has changed, and the universe is slowing down. So there would have been a time scale over which, around which the transition from the one behavior to the other took place. Incidentally, this is if it were to have grown exponentially, then it would have grown like this, right? Now, I'll come to something important, as I said, about the initial values. Let us see the initial condition. T is equal to 0 at x equal to 0. For this equation, you follow this point carefully now. For this equation, we said t equal to 0, x equal to 0. But for this equation, we could not write t equal to 0 at x equal to, we could not set the same initial condition. T equal to 0, x equal to 0. No, why not? Let us try to understand. You see, if I were to set x equal to 0, look at the general dynamic equation first. Follow this point extremely carefully. Look at the general dynamic equation first. If I set x equal to 0 at t equal to 0, then dx dt will be 0. Meaning at t equal to 0, there is nothing because x is equal to 0. And the growth rate is also 0, dx dt. You have nothing and there is no growth rate also. Non-zero, there is a 0 growth rate. So your system will not grow at all. And that is what you see. If you just look at this equation, x is equal to x naught e raised to plus minus at, right? Suppose I write x is equal to x naught is equal to 0, then x will be equal to 0 here. Is equal to 0 into e raised to plus minus at. Then thereafter, whatever be the value of time, e raised to plus minus at, whatever value it may have at whatever time, if x naught is equal to 0, x will remain 0 for all time to come. So regardless of, so if you see Okay, there's an important point I should like to make. Not that I have made it a part of the notes. There is something called a trivial solution. What do I mean by a trivial solution? A trivial solution is one in which, what is the solution of this equation, if I ask you? You'll say, oh, well, I'll have to integrate and all these things, and I shall find out. I'm going to say finally that this is the solution of the equation that has been provided. Dx dt is equal to plus minus ax. This is the solution. X is equal to x naught e raised to plus minus at. I said, oh, well, you have worked a lot, but there is, and I could have said that you did not ask me. I could have, if I were you, I would have said, you did not ask me what kind of a solution you're looking for. So I will say x is equal to 0 is also a solution. If x is equal to 0 is a solution, in fact. You see, if x is equal to 0, at dx dt is also equal to 0 in the early stages, if I say x is equal to 0, the right-hand side will be 0. And if x is equal to 0, dx dt is also equal to 0. So the left and the right-hand sides will match each other. There will be proper balance between the two sides. And you will have this x is equal to 0 as a trivial solution. But then that's not the kind of solution we are looking at. We can also look at, I mean, that's not an interesting solution, right? uh, the dynamics will be captured by what is known as a non-trivial solution, and this is a non-trivial solution. So simple as this system may look like, but there are many important points to discuss here. Okay, what about this thing? Now, here you notice something. I can, here for this equation, dx dt is equal to a plus minus bx, right? And I wrote t is equal to 0, x is equal to 0. You will ask me, why have I done that? Will there be no problem in doing such a thing? I said, no, not really. Just look at this equation. If at x is equal to, if at t equal to 0, I set x equal to 0, then this bx part will vanish. Right, but a and b are both non-zero quantities. A, in fact, is a positive quantity. So dx dt will still be equal to a, non-zero. So initially, even though at t equal to 0, there is nothing, which is to say x is equal to 0, the system has got a dynamic kick in the sense that it's got a non-zero growth rate set at the first, from the first. Therefore, even if it starts with nothing, it can still grow to higher values. That is the point. And in fact, in the early stages, when x is equal to very small, just see this equation, you can immediately figure out that the early growth would be linear. If x is very small, and let's say a and b are moderately valued quantities, if x is very small, you can neglect the bx against a. So dx dt is approximately equal to a. So what's the integral solution of that? Dx dt is approximately equal to a, and therefore x is equal to at. And that is what you have found. Early growth is linear. X is equal to at. Just get this one fact right. If you see an equation like dx dt is equal to a to begin with, then extra something, dx dt is equal to a constant, then extra something. Don't worry about that extra some functional part. If you see dx dt is equal to some constant to begin with, even if you set x is equal to 0, just check on that thing, that what will happen if I set x is equal to 0 in my autonomous function. Is dx dt is equal to 0 immediately? If dx dt is equal to 0 on setting x is equal to 0, then I should not set t equal to 0, x is equal to 0 as my initial condition. Because in that case, the system will become just a dud. It will not do anything. As in here, if you set x equal to 0, then dx dt will be equal to 0. So that kind of a system can't grow or do anything. It's just a trivial system, right? So just one point you check, dx dt is equal to a is the equation of arithmetic progression, and dx dt is equal to proportional to x is the equation of geometric progression, as in compound interest. Dx dt is equal to x is something that is in compound interest. If you have questions or anything, we can have a discussion of this thing at the end of the class. You can put it in the chat box. Dx dt is proportional to x is the compound interest, is actually the compound interest equation. It's exponential growth equation. Whereas dx dt is equal to a is the equation of simple interest. Just check in. I hope that in school arithmetic you would have studied all these things, simple interest and compound interest sums we used to do in class 5 or so, whatever. So that's the kind of thing that you have. Anyway, but in those days we did not, I mean, in class 5, nobody, I mean, you wouldn't have studied calculus, neither did I. But boiled down to this in terms of differential equations, an equation of arithmetic, the system obeying arithmetic progression is written as dx dt is equal to a. And a system obeying geometric progression is written as dx dt is equal to proportion constant into x, right? Positive constant into x, meaning plus a into x. And this is a geometric growth in proportion to the state. Okay, so I thought I'd just touch on these issues. Remember these two equations. Dx dt is equal to minus ax, not the plus part. The minus ax part will be very important. Dx dt is equal to a minus bx. That will also be very important in our physical systems discussion later. And later I'll also work on and soon I shall start on a nonlinear equation. But before that, I just briefly touch upon dx dt is equal to a plus bx because I've mentioned it, so I mean just work on it, right? A and b are positive quantities, so we can write this thing as dx dt is equal to a minus of minus bx. And so whatever solution we have found in the previous case, this is the solution that we found. X is equal to a by b into 1 minus e raised to minus bt. So wherever you have a b now, you substitute in this, wherever you have a b, for a system that obeys this general form, dx dt is equal to a minus bx. You start with this thing. This is the integral solution under this initial condition. A by b, 1 minus e raised to minus bt. So wherever you have a b there, you substitute it with minus b. So here, uh, this is the solution we found for a minus bx type function. And now it's a plus bx. So a plus bx can be decomposed as, I mean, reduced to a minus of minus b. So make b go to minus b in this formula. So a by minus b minus of e raised to minus of minus b will be plus b, e raised to minus bt plus 1. Then you put the minus b inside, and it will be a by b into e raised to bt minus 1. This is the solution of dx dt is equal to a plus bx. So then again, it's the same thing. When t is very much less than 1 upon b, b is a natural time scale of t. b is a natural time scale of t. Okay? So maybe I should stress on this point also. Why am I saying that b is a natural time scale of t? You just see this equation. I'm sorry, I should have stressed on this point. Look at this equation. I have got e raised to minus bt. Let me stress on this point again. B into t, small t. B into t must be a dimensionless quantity. You'll say, why should it must be a dimensionless quantity? I've written capital T is equal to bt. So, I mean, of course, from this equation, you can see that b will be 1 upon t, x by t here, and this should also be 1 upon t. But there is another way to argue for that. It is this. E raised to capital T minus capital T is e raised to minus bt. Now, if we just look at it as capital T, I've written this thing over here, 1 minus of capital T plus t squared by factorial 2 minus t cubed by factorial 3, etc. If t were to have a physical dimension, let us say length, let us say, if t were to have a physical dimension or time or whatever, just for simplicity, consider that e raised to some plus x or minus x, whatever this x, or in this case capital T, has got a mechanical dimension, t, a length, let us say, then what will you have in this exponential series? 1, which is dimensionless, minus of this thing will have the dimension of length, plus this will have the dimension of area, then subtract, this will have the dimension of volume. So can you ever do such a thing that add length and area and volume? You can't add these things. That will be dimensionally incompatible. So a function that is represented by an infinite series, you make a note of that point extremely carefully. A function that is represented by an infinite series, such as sine x, cos x, exponential x, log of 1 plus x, all these functions must have a dimensionless argument. What is the argument of a function? If I say f of x F is the function, x is the argument, right? If fx is equal to e raised to x, then x must be dimensionless, because written as an infinite series, if x were to have a dimension, then this would be a dimensional absurdity. You are adding higher and lower dimensions of the same, orders of the same mechanical dimension. You can't do that. So for dimensional compatibility, capital T must be dimensionless. And so what is capital T? B into small t. Therefore, B naturally defines a time scale. 1 upon B is the natural time scale of this system. So, that behavior is here. So 1 by B, from here to here, it's linear. From here to here, it's saturation. So within, around this natural time scale of the system, a transition is happening. So, okay, let's see now. You've got A by B, and then this thing is written as e raised to bt is 1 plus bt. I've neglected the higher powers of bt squared, bt cubed, all these things. So you have got the early growth is again linear. What about late growth? When you have late growth, look at this formula. T is very much greater than B. If T is very much greater than B, then T is very much greater than 1 upon B. Then if that is so, then B into T will be very much greater than 1. T is very much greater than 1 upon B. Therefore, B into T will be very much greater than 1. And e raised to a number that is very much greater than 1 will be a large enough number against 1 itself. E raised to 10, let's say, a very large number compared to 1. So you can neglect this 1 against it, and it will be e raised to bt. So as per this formula, x will be approximately equal to a by b, e raised to bt. You have neglected the 1 against it. So the late growth will now be exponential without any limiting behavior. And so if you were to plot and you can see, what about the early growth? When t is equal to 0, e raised to 0 will be 1, 1 minus 1 will be equal to x. So the function will start here at x equal to t equal to 0, x equal to 0. Early growth will be linear till 1 by b, and thereafter you will have an exponential growth without any limiting behavior. This is the point where the transition from the linear to the exponential growth phase will occur. This is exponential growth, whereas this is exponential convergence or exponential saturation. Saturation meaning you can't grow beyond the point, right? So that is what it is. So, and as I said, written for t going greater than infinity, there is no limit to growth. So that is what you will have. You'll have an exponential growth, and then you can see that the same system displays two kinds of dynamics, just as in the previous examples. Early growth is linear, later growth saturates. Here, early growth is linear, the later growth is exponential. So I have also drawn some dotted lines. This dotted line joined with this smooth curve would be completely exponential growth. This smooth straight track dotted with this, joined with this dotted straight track would have given you a completely linear growth. But the reality is that it's partly linear as given by this continuous line, and then partly exponential. Just a while ago, I mentioned the behavior of the universe. The behavior of the universe is probably early growth of the universe would have been exponential like that, and then the later growth has slowed down, become less than exponential. So probably it would be like this. Probably, but I'm not getting into that discussion in detail. So, but you can see that different kinds of, the systems can display, a system is capable of displaying different kinds of time-dependent behavior on different time scales, right? This is a small time scale, this is a large time scale. The transition is happening at t is equal to 1 upon b. And just for hypothetical consideration, I've written that if t goes to minus infinity, t will not go to minus infinity, t is positive time, then x will, we just see that if t goes to minus infinity, here in this equation, if t goes to minus infinity, then e raised to b being positive, t being minus infinity, this part will go to 0, and x will go to minus a by b. So x will go to minus. So the third quadrant for t less than 0 reflects the behavior of the this behavior, this kind of a thing. This kind of a thing has been inverted and brought into the third quadrant. Right, but that has happened because of that change of plus minus sign here. This is because of a minus bx, and this is because of a plus bx. Anyway, so I have finished this discussion of a linear system. I just discussed it with the help of two simple linear equations. One was dx dt is equal to plus minus ax, and the other was dx dt is equal to a plus minus bx. Simple as these two linear equations are, they can capture a good deal of physical problems, which we shall take up later. But I shall now want to go to a nonlinear system. Fx here is a linear equation, but what if the right-hand side is a nonlinear, meaning that it's no longer like the equation of a straight line, as in y is equal to mx plus c. So we shall see about that. Please just bear with me. I shall start a new presentation. At the end of the class today, please just wait for 1 or 2 minutes. I'd just like to discuss a few things about the Google Classroom, for which the link has been sent to you. Meanwhile, please just confirm that you can see the new presentation. Hello? Can
Yes, sir.
Okay, thank you. Thank you. You are able to see the new presentation. So first order nonlinear autonomous systems. What do I mean by first order? I told you, dx dt. Autonomous, the right-hand side is fx, that is autonomous. Now, so far we have talked about fx is equal to plus minus ax, or fx is equal to a plus minus bx. Now, I'm looking at a simple equation which is a combination of the two kind of things. Just look at this equation here. It is like x into a minus bx, right? So dx dt, I told you dx dt is equal to a plus minus ax, let's say, right? That's x, and then this other thing was dx dt equal to a minus bx or a plus bx. So now I can now take the product of the two things and write an equation like this. So x into a minus bx. So two linear terms, two linear functions I have multiplied, and I've got a new function, but this time it is nonlinear of the second order. This is nonlinear. This is in no equation of a straight line you will find a square term like this. So this is a nonlinear equation, of course. Immediately, noting that A and B are positive quantities, if you look at this equation, what did I tell you? What kind of initial condition should you be looking at? Just see, if you put x equal to 0 on the right-hand side, I'm sorry, if you put x equal to 0 on the right-hand side, then immediately dx dt will be equal to 0, right? So at t equal to 0, if you put x equal to 0, then your function is again a trivial, will again give a trivial solution. It's a no-go kind of a situation. There is no kind of no growth thereafter. So you immediately realize, I'm sorry, just a minute. I'm sorry. Can you please just confirm that you can see the presentation? Hello?
Yes, sir.
This is the nonlinear autonomous systems. That is what. If you, this is what, just, I'll check a few things, something. Okay, thank you. Yeah. So, immediately you'll realize that this can't be the equation of what we with an initial condition where t is equal to 0, you can apply t is equal to 0, x equal to 0. Anyway, we shall come to all that soon. Now what we shall do is we shall rescale the variables. We shall write dx dt is equal to ax into 1 minus bx by a. We take ax as a common factor, right? Then we take the a to the left hand side and we write it as dx is equal to d at x into 1 minus x by ab. We define k is equal to a by b. Okay. And then we define capital X as equal to small x divided by k, which is a by b. And we define a new rescale time, capital T is equal to at, right? if you just look at this equation, x you have over here, t in the denominator here in the left hand side. On the right hand side, you have x here. Therefore, immediately you realize that A must have the dimension of inverse time. So even if you have started, even without having worked with this equation, just by looking at its form, you would know what is going on. First, that you can't have an initial condition t equal to 0, x equal to 0. If you want to have any kind of a non-trivial solution, that is. Otherwise, you can still put x equal to 0 and dx dt equal to 0 and say that that is still x is equal to 0 is still a solution, even though it's a trivial solution. Okay. So anyway, so you immediately know what the nature of understand the nature of the initial condition. That is number one. And number two, you immediately know what the time scale of this equation will be. The time scale of this equation will be 1 upon a. 1 upon a will be the time scale. A will be equal to, a has the dimension of inverse time. So that is what it is. You can see a into t will be a dimensionless quantity. Therefore, capital T will be a dimensionless rescale time. Okay. Now, what we have done here is small x, capital X is equal to this thing, small x by k. So what we can do is that we can write small x is equal to capital X into k here and here also. Small x is equal to capital X into k. And then the two k's cancel on both sides, and there you have got a parameter-free nonlinear equation. Nonlinear as in the right-hand side is no longer just a function of the first power of x, it is capital X minus x squared. Actually, the right-hand side is the equation of a parabola, if you know recall your school conics clearly. Okay, now the next thing that we shall have to do is to separate variables. So take all the x type functions on one side, t type functions to the other side. And so you have dx by x into 1 minus x. I hope that you have not forgotten school lessons on partial fractions. So 1 by capital X into 1 minus x is to be broken into two partial fractions, capital A by x plus capital B by 1 minus x. And then you multiply this equation throughout by x into 1 minus x, and you'll get 1 is equivalent of a into 1 minus x plus bx. Now we put this thing, when x is equal to 0, follow carefully, when x is equal to 0, bx part will vanish. So you will have a into 1 is equal to 1, therefore a will be equal to 1. And when x is equal to 1, 1 minus 1 will vanish. So b into 1 will be equal to 1, therefore b will be equal to 1. So then the integral could be written as, by the use of the method of partial fraction, this integral can be decomposed into two integrals now, 1 by x plus 1 by 1 minus x. So dx by x plus dx by 1 minus x is equal to dt, and then you integrate it. So dx by x is a very simple thing. Here I'm just doing a little trick. 1 minus x I have over here. Instead of taking the minus sign outside, I'm putting a minus sign here and a minus sign here, as if the variable over which the integral has to be performed is not x but minus x. So when I've done that, then after that it's a very trivial thing. It's a very simple thing, not a very difficult thing. School calculus, integral calculus. This integral will be log x, this integral will be minus log of 1 minus x, then you have a constant, and this integral will be t, capital T, which I'm writing as log of e raised to t, and then a constant log c. Put all these things together and you'll get capital X by 1 minus x, it is equal to c into e raised to t. Now we shall write a solution. Here you can see you've got a bit of a mix-up over here, x divided by 1 minus x. I want to write a solution of x in closed form. That is to say, only x and nothing else on one side, and everything to do with t on the other. So let's see how we will do it. This is capital X, and then I'm taking this thing to the right-hand side, 1 minus x, so it will be c into e raised to t minus x into c e raised to t. Then this x business I'm taking to the left-hand side, so you have an x here, you have an x here. So capital X into 1 plus c into e raised to t is equal to c into e raised to t. Therefore, capital X is equal to C into e raised to t divided by 1 plus C into e raised to t. Well, I can write this thing I mean, I just divided this equation by C, or multiplied this equation with C raised to minus 1, E raised to minus T. This will give this thing as 1. This will be C raised to minus 1, E raised to minus T, and this will be 1. Anyway, so that is what you have. Initial condition, I mentioned to you earlier, it can't be T equal to 0, X equal to 0. X has to be a non-zero initial condition to begin with, and I have stressed that thing over here. Initial value is not 0 at t equal to 0. Okay. So we put the initial condition as t at capital T equal to 0, capital X is equal to x naught, or small x is equal to small x naught. We put that initial condition over here. E raised to capital T will be, when t equal to 0 will be 1, and capital X is equal to x naught. So x naught is equal to 1 divided by 1 plus c raised to minus 1. 1 plus c raised to minus 1 is equal to 1 by x naught. Therefore, just we shall now have to find the constant c. This is an arbitrary integral constant, right? We shall have to fix it. So 1 by c can be written like this, and so c is equal to x naught divided by 1 minus x naught. Right, and then we did not start with x naught. Our original variables were a and b. Ultimately, we shall have to go there. And this is the initial, but capital X naught is equal to small x naught by k. Why so? Because capital X has been defined as small x by k. So if I put a subscript naught here next to capital X, I shall do the same thing for the small x on the right-hand side. And so with that, this is our initial, I mean, this is the integration constant. Capital X is equal to x by k by rescaling. Now, as I said, it's always good to make your equation free of parameters, but ultimately you shall have to work with the parameters. I mean, the parameter values and everything will have to be finally put in your final integral solution. So we shall now have to go back there. This is our integral solution, right? Capital X is equal to 1 divided by 1 plus c raised to minus 1 e raised to minus t. So when we return to the variables x and t, small x and t, that is, capital X is equal to small x by k is equal to 1 divided by 1 plus c raised to minus 1 e raised to minus capital T is at. Okay. So when t goes to infinity, for any initial value, you don't know, any initial value, of course, any initial value which is not equal to 0, that is important. For any initial value, whatever you start with, you just see this thing, e raised to minus at. When t goes to infinity, this thing will go to 0. C is not infinity or anything, so 1 by c will be a finite quantity. C is equal to x naught by k minus x naught, and 1 by c will be accordingly a finite number. So finite into 0, this part will be 0. So x will go towards k. And what is k? K was defined as a by b, as here when we rescaled. K was defined as a by b. And so when we go this way, small x will be equal to a by b. Okay. Now what we shall do is that we will look at this equation. We now recast this solution. You have e raised to minus at in the denominator here. Multiply both the numerator and the denominator with e raised to plus at. So this will be k into e raised to plus at divided by 1 into e raised to plus at will be this, and this part will cancel. And c raised to minus 1 from here will be k minus x naught divided by x naught. Okay. Next task is that I'll multiply both the numerator and the denominator by x naught. Okay, so k into x naught e raised to at divide then x naught into e raised to at plus k minus x naught. Okay, next you capture these two terms containing x naught e raised to at and minus x naught. So I have captured that x naught e raised to at minus 1, x naught being a common factor. And then Once I have done that, I have divided both the numerator and the denominator by k, and so the numerator will be x naught e raised to at, and the denominator will be 1 plus x naught by k into e raised to at minus 1. This is the final integral solution, where k, of course, is equal to a by b. Okay, let us see what happens when t is equal to 0. When t is equal to 0, e raised to at will be equal to 1. So x will be equal to x naught divided by 1 plus x naught by k, e raised to at will be equal to 1. 1 minus of 1 will be 0. So the denominator, this part in the denominator will vanish when t is equal to 0. So x will be equal to x naught as we began with. Now comes something important. When t is very much less than 1 upon a, the natural time scale in this system is 1 upon a. So when t is very much less than 1 upon a, what will happen is e raised to at will be equal to, let's see now, 1 plus at squared by factorial 2, all that thing. I'm writing at as t divided by a raised to minus 1. So when t is very much less than a raised to minus 1 or 1 upon a, that condition we have. So then the square and every subsequent power can be neglected against the smaller power, right? Because at is a small number. T into a into t is a number much smaller compared to 1. So e raised to at can be written as 1 plus at, right? Now here you have got e raised to at minus 1, e raised to at minus 1. That is what you have. So e raised to at minus 1, this part will be approximately equal to at. And so this solution, which is the exact general solution, in the early stages when t goes to 0 but not exactly equal to 0, uh, we can get e raised to at minus 1 as at, and this is how we will write the equation. Now, let us look at the behavior of this statement that we have here, the mathematical formula. Follow the logic a little carefully. Exponential growth is always faster than linear growth. I hope you know that fact. You appreciate that fact. Exponential growth is faster than linear growth. So, in the early stages, the growth will be dominated by the exponential part up here compared to the linear part. This is linear. At is linear, right? This will be dominated by the exponential part instead of this approximately linear part in the denominator. So that is what has been written. The dynamics is dominated by e raised to at in the numerator, not e raised to at minus 1 in the denominator. As a result, it would look like that the early growth is approximately exponential. Approximately, it looks like that it is going to be an exponential growth. So you would think that, okay, we are growing very rapidly. And of course, must have an initial value, x subscript not equal to non-zero, is a non-zero number. X naught is not equal to 0. Okay. But can we simulate the exponential growth? I've written something over here. Let me read that out first. The exponential early growth is also simulated by k going to infinity. In the early stages, k will appear large, especially for small values of b. Let us see, what do I mean by that? K going to infinity. If k goes to infinity, what is k defined as? K has been defined as a by b, right? So to make k go to infinity, b should go to 0. Follow carefully. So if I want to have k infinity, b should go to 0. Well, b is not 0 exactly, but b can be very small. But suppose if b is equal to 0, in this is the equation that we started. If b is equal to 0, then dx dt will just be equal to ax, and that is what you will see. you will have a purely exponential growth. Dx dt is equal to ax, you integrate it, and you'll get x is equal to x naught e raised to at. We just discussed that thing in the case of only the linear part will remain. When we discuss the linear autonomous system, we discuss this point. But b is not 0, but it's still a very small number. And so the smallness of b makes k look very large, as if it is going to infinity. In that case, just look at this formula. If k is very large, as if k is infinity, then any number divided by infinity will be 0. Let's say k is infinity, x naught by infinity, x naught into e raised to at minus 1 for whatever time or anything. K is being infinity, this part will anyway be 0, and you'll just have x is equal to x naught e raised to at. So I have written that thing, that the early exponential growth is also simulated by k going to infinity. That is to say, when b is a small number. Okay, this sort of a behavior, by the way, I'd just like to mention something again in passing as an application. This kind of a behavior, dx dt is equal to ax minus bx squared, is applied to model population growth of species, including human species, right? So we shall see how it happens. Like in the early stages, any species will grow very rapidly, exponentially. Why exponentially? Why not linearly? Because, as I said, this is an equation of geometric progression. You can't have a species growing out of nothing. Arithmetic progression, you can start with t equal to 0, x equal to 0, and you can still have something. But you can't have a species coming out of nothing. A species must have an initial few members, right? So you'll have to start with a non-zero value of the members of the species, and thereafter you will see a robust exponential growth. But then no species grows to infinitely large in number. If you continue growing on an exponential path, you will keep growing without any limit. But that doesn't happen because the Earth is a finite system, and your growth would be braked because of the limitness or the finiteness of the ecological niche or the environment in which you live. Incidentally, these days there's so much talk. There's so much talk about population growth and environmental degradation, all those things. So you can see, if population grows exponentially and rapidly, nature has her own way of putting a brake on it, because nature has got to find balance. So environmental degradation will cause deaths among the members of species and all that, and again, the growth rate will saturate. Anyway, that's a different discussion. But I'm saying that this equation has got serious applications. It is known as the logistic equation, LOGISTIC. By the way, in your, let me just remind you of something. In your mathematics problem sheet, I have supplied two sets of problems in your mathematics theory problem sheet. One's equation number, so the first set is on autonomous equations. Question 5 is this sort of an equation, ax minus bx squared form. And question 6 in set 1 is a minus bx form. Just check the linear equation that we discussed earlier before this. That is question 5, and this is the nonlinear equation. That's sorry, that was question 6, and this is the nonlinear equation in question 5. So we are discussing the theory solution of that right now. So anyway, now you can see then again, so there is a difference. I mean, there is a time scale over here. Early growth is exponential, as we can see, but later growth on long time scale will saturate to a limiting value. X will go to k, and early growth will show as an exponential growth, not a linear growth. As in the case of a minus bx, we saw an early linear growth and then a saturation. But here we are seeing an early exponential growth and then a saturation. Why are we seeing an early exponential growth? Very simple thing. For small values of x, let's say x squared can be neglected against x, because the higher power can be neglected against the lower power. So if this thing drops out, then you will have dx dt is approximately equal to ax, and the early growth will show exponential behavior. Whereas in the case of an a minus bx equation form, If you neglect the bx, then dx dt is equal to a is the equation, and x will be equal to at. So we shall now have to see, plot how the growth changes from one mode to another. We'll show, go to exponential growth and all that. So let's see now. We will do it in a slightly different manner. We have this equation dx dt is equal to x minus x squared. We rescaled our equation for the purpose of integration, dx dt equal to x minus x squared. So we will go back to that equation. Dx dt is equal to x minus x squared. Take the second derivative of this thing, d2x dt squared is equal to df dx into dx dt. And dx dt is equal to f, right? Where f is x minus x squared. So df dx is equal to 1 minus 2x. So now let us see. Follow this point carefully. When can d2x dt squared be equal to 0? Either dx dt is equal to 0 or df dx is equal to 0. One of the two things. Df dx is equal to 0 or dx dt is equal to 0. Now, when df dx is equal to 0, d2x dt squared is equal to 0. But when I told you dx dt equal to 0, d2x dt squared will be equal to 0. This will be 0. This is also equal to 0. We are looking at a condition whereby df dx is equal to 0, but dx dt is not equal to 0. So when dx dt, we are looking at that condition. When dx dt is not equal to 0, we can still have df dx is equal to 0. So that d2x dt squared is equal to 0. Now, starting from x equal to x naught to x equal to 1, dx dt is always a positive quantity. How can we say that? Just look at this equation. When you start from x equal to x naught and go to x equal to 1, this number will always remain a positive quantity. Dx dt is a positive number, right? So basically then, if dx dt is equal is a positive number, 1 minus 2x must be equal to 0 when d2x dt squared is equal to 0. So that is the condition. So 1 minus 2x is equal to 0 will give us this condition, x is equal to half. So when x is equal to half, fx has a turning point. Now let us follow this point carefully. If x is less than half, if x is less than half, df dx is equal to 1 minus 2x will be a positive number. And if x is greater than half, df dx is a negative number. At x equal to half, df dx is equal to 0. So since dx dt is equal to 0 for any finite value of x, right? If that is so, and for x greater than x less than half, d2x dt squared will be a positive quantity. That is, growth will be happening at an increasing rate. What do I mean by growth happening at an increasing rate? Let us follow this discussion carefully now. I give you a function. In this case, we have got x as it depends on t. You follow this point carefully. How will you know that the function is growing? The function will be growing if its gradient is positive, if its first derivative is positive. As t increases, x increases. Therefore, dx dt or delta x by delta t will be a positive number, both increasing, right? Incidentally, if the function were to decay, then as t increases, x will be dx will be negative, x will decrease. So delta x will be a negative quantity, meaning the initial value will be larger than the final value in every step. So that is, so for growth, you will have a positive first derivative. For decay, you will have a negative first derivative. But here we are not worrying about decay, we are worrying about growth only. But growth can happen in two ways, three ways, in fact. Just consider the equation of a straight line. Y is equal to mx plus c. dy dx is equal to m. Let us say both m and c are positive numbers, right? At least m is a positive number. Dy dx is equal to m. So if m is positive, then dy dx it has a positive gradient. Therefore, y is growing as x is growing. Fine, we have growth. What about d2y dx squared? Since m is a constant, d2y dx squared is equal to 0, meaning that this is growth at a constant rate. dy dx is constant, m. But if d2y, and that is shown by d2, the second derivative being equal to 0. But if d2x dt squared is positive, then this is growth at an increasing rate. But when x becomes greater than half, d2x dt squared is negative as per this argument. d2, because df dx will be negative. So this thing will be negative. Although first derivative is positive, second derivative negative means that the growth is occurring at a decreasing rate. Hence, before x equal to half, uh, you will have, by the way, I made a slight error over here. It should be capital X less than half. It is there in your correction. Capital X less than half. This should also be capital X greater than half, right? I just hurried writing. Capital X less than half, capital X greater than half. It is there in, there's a list of corrections. So before x equal to half, growth is exponential, and beyond x equal to half, capital X here, growth saturates as x goes to 1. At x equal to half, the nonlinear effect minus bx squared starts to take effect, right? We find its time by... So what is the time scale for this? See, if this nonlinear term were not there, dx dt would have had a completely exponential growth. But as x is growing, x squared is also becoming more and more important, right? So as x squared is becoming more and more important, the negative term minus bx squared is becoming larger and larger. If without this negative term, you would have just had dx dt is equal to ax. But as x is growing in value, bx squared is becoming more and more significant. And as it is becoming more and more significant, with a minus sign before it, overall, the right-hand side is progressively reducing in value, a minus bx squared. So because of the largeness of x, slowly this term is applying a brake on the growth rate. Because if the right-hand side becomes progressively, starts grinding down to a slow halt on the right hand side, then dx dt will also show that behavior. Dx dt will also slow down, right? So that is what is happening. So we now have to find a time scale for the transition from an early exponential growth to the later braking behavior. How will we find that time scale? What we have found is that this early exponential growth is sustained till capital X is equal to half, because up till then you will have d2x dt squared with a positive sign. Beyond that, capital X will grow to, I mean, d2x dt squared will have a negative sign. So it will be growing because the first derivative will be positive all along, but it will grow at a slower rate, at a decreasing rate. What is the time for this thing to happen? We already have a formula. X, capital X is equal to this thing, 1 divided by 1 plus c raised to minus t e raised to minus t. So we know that capital X is equal to half is the transition behavior. So putting half over here, we should be able to find the time scale for the nonlinear effect to happen. So let us see. That is what we are doing. Capital X is equal to half is equal to 1 plus 1 divided by 1 plus c raised to minus 1 e raised to minus t, capital T, nonlinear. What do I mean by nonlinear? Because this is a time scale whereby the nonlinear effect of minus bx squared starts showing its significance. So this equation can be solved by taking an inverse. I take 2, I mean invert this, 2 is equal to 1 plus c raised to minus 1 e raised to minus t nonlinear. 2 is equal to, I mean this 1 I can take to the left hand side, it will be 1 plus c raised to minus 1 e raised to minus tl. So invert that again. So c into e raised to t n l is equal to 1, and therefore t n l will be equal to log of 1 by c, and log of and 1 by c is equal to 1 minus x naught by capital X naught, and capital T is equal to a into small t. So a into small t n l is equal to log of k minus x naught by x naught. Okay, and so t n l will be equal to 1 upon a log of k by x naught minus 1. Now let us just look at this thing. uh, Nonlinear time must be a positive quantity. Time is a positive quantity, whatever, linear, nonlinear, whatever. Realistically, that is what it should be. So if that should be positive, then log of this thing, k by x naught minus 1, should also be a positive number. But for log to be a positive number, its argument must be greater than 1, because log of 1 is equal to 0, log of a number less than 1 is negative, and log of 0 is minus infinity. Argument of logarithmic functions cannot be negative, right? So this thing must be positive anyway. But since you're talking about time, and a has also by definition been defined to be positive, k by x naught must be greater than 1. Therefore, k by x naught must be greater than 2, and so x naught must be less than k by 2. So the initial value x naught must be less than k by 2 for a strong exponential growth at early times. So let me now look at the graph of this thing. Let's see what is it. I've talked too much. What did I mean by early exponential growth, nonlinear time scale? All of these things will become very clear from the graph. Here I have plotted the function. You start from a non-zero initial value. Early growth will be exponential. Had the nonlinear term minus bx squared not been there, then this exponential growth would have traced this dotted curve and kept going on forever to higher and ever higher values. However, minus b x squared applies a brake on the growth. As a result, at this point where you have the nonlinear time scale, because minus bx squared is the nonlinear term, a transition to a slow saturation behavior takes place. Here, this is the point I'm trying to make. Now you follow carefully. d2x dt squared will be positive when you have growth at an increasing rate. Here you can see it is concave upwards. Had it been a straight line, the second derivative would have been 0. If the second derivative is greater than 0, positive number that is, you will grow like this. A straight line will grow like that. And here it is concave downwards. Second derivative being negative, meaning that here it is growing at a decreasing rate. And here it is growing at an increasing rate. So this statement has been made over here. d2x dt squared, growth is at an increasing rate. For, again, I mentioned this is capital X, this is capital X. Thereafter, at capital X equal to half. What is capital X? Capital X is small x by 2. So if capital X is equal to half, small x will be k by 2. So beyond k by 2, you have growth at a decreasing rate. So this, and the time corresponding to that will be the nonlinear time scale, t nonlinear. This is the value. So after TNL, growth slows down. This is what you have. If x naught is less than k by 2, if your initial value is less than k by 2, then the early growth will be exponential. Here, what if I were to have, now you can very well ask me, I mean, I can anyway have the initial value to be higher than k by 2, right? I said that if x naught is less than k by 2, then you'll expect a strong early growth, exponential early growth. But suppose my initial value was here. If your initial value was here, then anyway, this argument, this nonlinear time scale business will not apply. You're starting with a large x value. If you're starting with a large x value, then in that case, starting with a large x value, you can't anyway neglect this part, right? As a result, even from these early stages, your growth will be a slow decreasing rate growth. So whatever you have here, if you start with x naught, you come here, and then you have this concave downward curve. If you start above k by 2 line, then it will be as if that this curve will be shifted here, and thereafter you'll have this saturation behavior. So if your initial condition x naught is between k by 2 and k, then growth happens all the time only at a decreasing rate. That is what you have. And then the last point is that growth stops at k x equal to k, where dx dt is equal to 0. So this will be a saturation thing. It will keep going. This is known as the carrying capacity. One last point before I stop, but you please stay on for 2 or 3 minutes more. One last point before technical point before I stop is that this value of this quantity k is called the carrying capacity. This is a term that has been taken from population dynamics. How much population of a species can a certain environment or a certain ecological niche carry? What is the maximum capacity of that ecological niche to carry a population? So that is known as the carrying capacity. So I have discussed all these things. So you just have all these notes and all these things. So as I said, this thing, if capital X is less than half here, that part corresponds to this growth. If capital X is greater than half here, df dx is negative, that part corresponds to this. So later maybe we can have a more detailed discussion on these things when I talk about something about mathematical theory, but not now. So I shall stop the technical discussion over here. So this finishes your theory, mathematical theory for the first set of mathematical theory questions. All the relevant theoretical discussion is now over. I'm stopping the sharing. I'd just like to discuss a few other points. It is that last